Good morning, everyone.
Good morning, sir.
Okay, today is the lecture number 2 of this advanced concept in steel technology subject, and today we're gonna discuss about these topics, which are the today's menu. And the first one is the characteristics of different plain carbon steels. Okay, so we have started about the introduction to steel, and we have discussed about the definition, and we have discussed about some classification of plain carbon steel, and also we have seen the evolution of microstructures on doing equilibrium cooling of plain carbon steels. And today we'll continue with that only. And today also we'll discuss about some alloy steels and their classification. So characteristics of different plain carbon steel. Before moving into that, let me recall few things of previous class. This topic is other alloying elements or impurity elements in steel and steel composition. As we have discussed, in case of simple plain carbon steels, we have some impurities, right? Carbon is an impurities as well as an alloying element, and it will be an impurity if the concentration will be higher, obviously, and if it will be an alloying element if the concentration will be in the limit. A particular limit is there, safe limit, right? So if somebody will ask when to say that these elements are impurities and when to say these elements are alloying elements, so the simple concept is that if they are below the safe limit, if their concentration is below a safe limit, and then it is an alloying element. If their amount is above the safe limit, it is not an alloying element, it is an impurity simply, right? So basically this carbon, manganese, uh, and silicon, you can call them as an alloying element, you can call them as an impurities, right? And you understand the concept behind that. But the problem is what the phosphorus and sulfur are basically considered to be an impurities. Basically they are impurities, they are not alloying elements, right? Sulfur can be an alloying element sometimes. Suppose we need an high machinability, right? Suppose we want our steel should have high machinability means able, how easily you can machine it, how easily you can give a shape or you can cut it, right? So if the sulfur content will be high, it can be easily machined. So sulfur improves machinability in steels. So basically sulfur is an impurities, because you understand in the previous lecture we have discussed what is the problem with the sulfur. If the sulfur concentration will be higher in the steel, it start reacting with the iron, and once it react with the iron, it form iron sulfide. So in the molten state of steel, you will be having iron sulfide and iron basically, or steel and iron sulfide, right? And upon solidification, what happens? Since iron sulfide is a low melting point substance, or it is an eutectic compound, it will solidify along the grain boundaries. So that means a thin film of iron sulfide will be there along the grain boundaries, right? So what will happen? Inside the grain, it is steel, that is iron, and along the grain boundaries, it is FeS, iron sulfide. And iron sulfide is a low melting point substance, or it is a eutectic substance, right? But steel or the iron is a high melting point substance. So the moment you are doing hot rolling, right, hot working, then you have to raise the temperature of the steel to 950 or 1000 degrees centigrade. So what will happen? Along the grain boundaries, the melting will happen, because iron sulfide is a low melting point substance. Along the grain, there will be no melting. So what will happen? The grain will get separated from one another. So mechanical strength will reduce during hot rolling. So that is the main issue with that. That is called hot shortness effect, right? Similarly, the problem arises when phosphorus is also high, right? So important point, let me tell you here is, we can control the deleterious effect or ill effect of sulfur. The sulfur deleterious effect or ill effect can be controlled just by adding manganese into the steel, right? So always we want, if suppose it is difficult to remove sulfur from the steel, we can do what? We can add manganese into the steel. So manganese will take care of the ill effect of the sulfur. So basically what we want manganese by sulfur, or manganese divided by sulfur should be higher. The ratio should be higher in the steel. so that the manganese will take care of the sulfur problem, right? Because you understand why, how it can be solved. Because if you add manganese, then sulfur will not react with iron. Sulfur will start reacting with manganese, and it will form manganese sulfide, and manganese sulfide have high melting point. Iron sulfide have low melting point. So the problem is solved. So the moment you are doing hot rolling and manganese sulfide will be there will be no melting along the grain boundaries, because manganese sulfide will be there and manganese sulfide have high melting point, right? So that is the solution to that. And let me tell you an interesting line here: how to decide how much manganese you can add into the steel to take care of the sulfur, right? It's very interesting. You can simply multiply the amount of sulfur into 25. That is very interesting. Suppose you have 0.02 weight percentage of sulfur, right? So how you will decide how much manganese you have to add? Simply multiply 0.025 into 25. You will get 0.5 weight percentage of manganese. So just add 0.5 manganese, zero point 0.5 weight percentage of manganese into the steel, and that will take care of your sulfur, right? Anyway, so we'll move to the phosphorus. Phosphorus, see, if you remember how steels form, we get steel from iron itself, right? We will first make iron, then from iron we'll make steel, right? So if lot of phosphorus will be there in your iron, then you have to imagine that a lot of phosphorus also goes into the steel. So that is the main issue, right? So we try to remove phosphorus as much as possible during steel making process, right? And there is no alloying element who will take care of the phosphorus. Here manganese will take care of the sulfur, but phosphorus will be not taken care of by any other alloying elements. So basically what happens, if phosphorus content will be high, phosphorus will start reacting with iron to form iron phosphide, Fe3P. Huh. And this iron phosphide is also a brittle substance, or basically it is a brittle substance. It is a low melting point substance, and it is a brittle substance. So the problem is what? The phosphorus will leads to cold shortness. Cold shortness means when you do cold working, or basically warm working, or working of metals, or you are deforming your steel at low temperature or very less temperature, the crack will form along the grain boundaries, because this Fe3P also 3 Fe3P, this iron phosphide also gets segregated along the grain boundaries. Why? Because they are low melting point substance. You have to remember this concept that any substance which have low melting point will always segregate along the grain boundaries. So you understand the final melting is happen along the grain boundaries, or the final liquid which will solidify will happen always along the grain boundaries, not inside the grain. So this is all about your impurities and their problems. Fine. So now we'll move to the characteristics of different plain carbon steels. So as we discussed, the plain carbon steel may be low carbon, medium carbon, and high carbon, and these are their advantages and disadvantages. So you can understand, if the as we remember in the physical metallurgy, if we increase the weight percentage of carbon in the steel, the strength will increase, hardness will increase, the ductility will decrease, right? And the toughness, if you are talking about, the toughness also increases, then it falls again at high consumption. Similarly, the strength will increase and it will decrease again due to formation of cementite, right? So the advantage of low carbon steel is it has high ductility, or it has good workability. Workability means you can call good formability. Good formability means you can give them a good shape according to your requirement. You can deform it to a large extent, right? It has good weldability. This is very interesting. You have to remember the weldability characteristics of the steel depends upon the weight percentage of carbon. It is just inversely proportional. If the carbon concentration will be more, the weldability nature will be decreased, right? Anyways, so what are the disadvantages? It has poor strength, poor toughness, as I told, poor response to the thermal heat treatment, right? And they have low hardenability. This is very important. Hardenability characteristics, very important. Let me ask anybody from you. Can you people know what is hardenability characteristics of steel? Can you people tell me in a short way? Any of you can tell me quickly. If you know, if you don't know, then I'll move on. Hardenability characteristics means the steel should form martensite everywhere, starting from the center or starting from the core of the steel to the surface of the steel. Everywhere martensite should form upon slow cooling. That is called hardenability characteristics, or the susceptibility of a steel to form martensite throughout the cross sections, starting from the center of the steel body to the surface of the steel body, or from the core of the body to the casing or the case, right? So that is called hardenability. Obviously, we want martensite because martensite is a phase, or it is a microstructure which provide high strength to the material or high hardness to the material, right? Anyways, medium carbon steel, you can see the carbon concentration is somewhat high, so it has good strength, good toughness, and it has a good it shows good response to heat treatment. So this is medium carbon steel. And high carbon steel, it has good strength, high hardness, and high wear resistance. This is very interesting part. It has high wear resistance and high abrasion resistance. If you want, you can write high abrasion resistance. Abrasion resistance. You have to remember, this is very interesting. If you increase the carbon percentages, the steel become more harder and more harder, and because due to formation of cementite, right? So what happens if cementite is a very hard and brittle phase, basically, right? But you can convert your cementite into nodules, basically, in the nodular cementite, right? Which can give you some toughness, which can give you good strength also, right? Instead of network of cementite, you can convert the network of cementite into nodular forms, spheroidal forms. They will give you more toughness, more strength, right? Your brittleness property will decrease due to formation of the spheroid of cementites. So what happens? The important point is the wear resistance increases, abrasion resistance increases, right? But pore toughness, as I told, if network of cementite will be there, the toughness will reduce to a large extent. So that is the point. Okay. So next topic is application of different plain carbon steels. So these are some applications. You can see low carbon steel. You can produce sheet. You can produce strip. You can produce some structural sections. You can do case hardening, right? Case hardening means like you can do your deposition of carbon on the surface, right? To make the surface very hard. Then medium carbon steels, you can make gears, connecting rods, laminated springs, and high carbon steel, you can make tools out of that. And pre-stressed concrete wires. These are some important application of those steels. Okay. Now this is a very interesting part we'll discuss, the limitation of plain carbon steels. So as I told, if we have plain carbon steel where the carbon is the major alloying element, or the properties of the steel is governed by the weight percentage of carbon. So that is plain carbon steels. So what are the limitations? The major limitations are here. The first one is the properties, that means the mechanical strength reduces at high temperature. So this is one of the property, one of the main limitations. Second one is they have poor hardenability characteristics, right? We may discuss this one in coming lecture if you want. All of you know the TTT diagram and CCT diagram, right? And the one is poor corrosion and oxidation resistance. They will get easily corroded and get easily oxidized in a corrosive environment or at high temperature. Then there is a major loss of hardness on tempering. There is a heat treatment called tempering heat treatment, which is always followed by hardening heat treatment. Because in hardening heat treatment, we produce martensite, and that martensite is brittle in nature. We cannot put the steel into application directly. So what we need to do, we need to do tempering heat treatment, and tempering heat treatment will bring some ductility. It brings some toughness in the material. The brittleness property will get reduced on tempering. But doing tempering, what happens? If it is a low carbon steel or plain carbon steel, the hardness and the strength will reduce to a large extent. So these are the main limitations of it. So now we'll move to the alloy steels and alloy steel classification on various bases. So if we have plain carbon steels, then why we need alloy steels? So alloy steels are produced by adding alloying element into the steels. We can add chromium, we can add nickel, we can add tungsten, vanadium, niobium. Depending upon our requirements, we can add alloying elements, because each alloying elements have a particular role to play in the steels. Some may increase hardness, some may increase toughness, some may increase your strength, some may do other things, right? So depending upon our requirement, we are adding alloying elements into the steel. So alloy steel is that steel which contain a little amount of carbon and other alloying elements, or a single alloying elements, right? Which are basically non-ferrous elements. So you understand, since these are the limitations of plain carbon steels, so to take care of those limitations, we are making alloy steels. That is the answer. So that is the need of alloy steels. Alloy steel will take care of these limitations. It will improve these properties. We'll see that soon. Okay. Now the classification of alloy steel. So alloy steel can be classified on the basis of these things, on the basis of amount of alloying elements, on the basis of microstructure or phases present in the steel, on the basis of composition, what kind of alloying elements are present, and on the basis of applications area. So on the basis of this one, on the basis of amount of alloying element, we can have low, medium, and high. So we can have low alloy steel, medium alloy steel, and high alloy steels. And this classification is on the basis of, if the weight percentage of alloying element is below 5 weight percent, it is called low alloy steel. If the weight percentage of alloying element is between 5 to 10, it is medium alloy steel. And if the weight percentage of alloying element is above 10 weight percent, it is high alloy steels. Then on the basis of microstructure or the phase present in the steel, we can have a ferritic steel. You can write ferritic. We can have martensitic. And we can have benitic. We can have austenitic. We can have precipitation hardening steel. So on the basis of microstructure, that means on the basis of their, basically, if you look into this one, on the basis of the matrix, what kind of matrix is there? If ferritic matrix, it is ferritic. If martensitic, martensitic matrix. If benitic, benitic. Austenitic, austenite will be there. And precipitation hardening means precipitation will be there. Some precipitate will be there, which will take care of the strength, basically. So then on the basis of composition, that means what kind of alloying element is present. Suppose we can have a chrome steel, we can have a nickel steel, we can have chrome plus nickel steel, sorry, chromium and nickel steel. We can have chromium, nickel, molybdenum steel, and etc. Right? So that means if your steel containing chromium as a measuring alloying element, only chromium, it is a chrome steel. If it is nickel, then it is nickel steel. If it is chromium, nickel, then it is chromium nickel steel. If it is chromium, nickel, molybdenum, it is chromium, nickel, molybdenum steels. So finally, area of applications. So for example, if we can classify the steel into electric steel, electrical application, we can have electric steel, we can have magnetic steel, we can have corrosion resistant steel, we can have high temperature steel, or heat resistance, better, right? Heat resistance. So on, etc. So on, depending upon the what kind of nature they have, they can be classified also on the basis of nature or on the basis of area of application. Electrical steels, magnetic steels, corrosion resistant steels, and heat resistant steels. And let me tell you here, interesting point here. Magnet, if you have seen your kitchen utensils, they are not get attracted by magnet. Basically, why? Because they are austenitic steels. If you have an austenitic phase in the steel, they are non-magnetic in nature, so they are not attracted by. So basically, ferritic steels and martensitic steels are attracted by magnet. And let me tell you one interesting point here. You have some knowledge about electromagnetic steering, right? So if you want to do electromagnetic steering of liquid steel, so in that case, what happens? We need a container, or that is container means we need a ladle. That ladle should be made up of austenitic steel. It should not be made up of this ferritic or this martensitic steel. Because can anybody tell me why the ladle should be made up of austenitic steels if we need electromagnetic steering of liquid steel, not ferritic, not martensitic?
Sir, can you repeat?
Why your ladle should be made up of austenitic steel rather than ferritic and martensitic steel to do electromagnetic steering of liquid steel or molten liquid? Few seconds before I told you austenitic steel is a non-magnetic steel. If the container will be made up of austenitic steel, then the container will not rotate. All we want is to rotate the or revolve this liquid steel, right? So it should made of austenitic steel. If it will be made of ferritic or martensitic, then the container will rotate. So it will not our purpose will not fulfilled, right? Okay. Anyways, so these are the classifications. Then significance of alloy steels over plain carbon steels. So as I told, the alloy steels have a lot of advantages over this plain carbon steel. So that is why we are making alloy steels, right? The most important advantages are here written over here. One is the improve high mechanical strength, improve high temperature mechanical strength. It improves hardness. It improves wear and abrasion resistance, improve corrosion and oxidation resistance, improves hardenability characteristics, improve fatigue strength. So improve it also for stabilizing some definite phases. Definite phases means you can stabilize austenite. We can stabilize austenite phase. We can stabilize ferrite phase, like this. We can stabilize, or it can improve stiffness. Then it provides resistance to softening on tempering. As I told, on tempering heat treatment, the material gets softened. So we can prevent softening by adding alloying elements. So these green lines are basically important for heat treatment purpose. Whenever we need heat treatment and we can improve the properties, these are very essential. Okay, let me tell you, otherwise if you want, here improves hardenability characteristics, because upon addition of alloying elements into the steel, the nose of the C curve of the TTT diagram moves towards right side. So what will happen? Upon slow cooling, you can produce martensite, right? So that means the hardenability characteristics increases. That is the point. Here stabilizing some phase means if you want a big region of austenite, right, then you can stabilize them by adding some austenite stabilizers. Suppose nickel, you can add nickel. You can add nickel is one of the best austenitic stabilizer. You can add nitrogen. You can add manganese. Those are austenite stabilizer, right? And what about this ferrite stabilizer? If you remember, the ferrite stabilizer are chromium, your molybdenum, tungsten, right? And other austenitic stabilizer is like you can add chromium, copper. Copper is a good austenitic stabilizer, right? So you can add those alloying elements and you can stabilize those phases. Right? And softening characteristics provide resistance to softening on tempering, because you understand some alloying elements form strong carbides. And once they form strong carbides, they pin off the grain boundaries. So once the grain boundaries is pinned up, the grain growth will be prevented. And once the grain growth will be prevented, the grain will not become coarser. So grain will still remain finer during heat treatment. So what will happen? The strength will not get reduced. That is the point. Yeah. So these are the important points. Okay, fine. Next one, the limitation of alloy steel. So alloy steels have certain limitations. The major limitation is it is expensive, right? If you compare the alloy steel and plain carbon steel, alloy steels are expensive because these alloying elements are costly. This nickel, chromium, vanadium, tungsten, molybdenum, niobium, right? They are very expensive in nature because the cost of production is very high, and the point is the availability in the nature is also very low, so they are expensive. The second one is yes, and the processing cost is also high, right? You need some processing expensive equipment, expensive processes to process them, so they are expensive. These are other two major limitations. One as major limitation is the alloy steels. Some of the alloy steels, not all alloy steels, some of the alloy steels which contain chromium, nickel, silicon, manganese, they're prone to temper embrittlement or temper brittleness. So what is this temper embrittlement or temper brittleness? The thing is what, on doing tempering heat treatment, what happens, suppose there is a range of tempering heat treatment like 400 degrees centigrade to 650 degrees centigrade. If you, some certain steels which contain these alloying elements, and if you are doing tempering of those steel at a range of 400 to 650 degrees centigrade, the toughness will reduce to a large extent. So that is called temper embrittlement or temper brittleness. And there is a solution to that. If you want that, the solution is what, you have to do tempering just above that heat treatment, just above that particular temperature, like above 650, and you have to do sudden cooling or faster cooling of them. That then temper embrittlement can be minimized or can be neglected easily. And these impurities or these alloying elements also cause temper embrittlement in the certain steels. Another one is this is another interesting point. Alloy steels have a greater tendency for retained austenite. So you people know what is a retained austenite. So retained austenite forms basically when we are doing quenching of our steel. We do quenching of steel means very fast rate of cooling of steel from the austenitizing temperature. So the moment you do quenching of steel or you do faster cooling of steel, or sometimes you want martensite in your steel, so what you need to do, you need to do quenching or you need to do fast cooling of the steel from the austenitizing temperature. So you want your austenite to transform into 100% martensite, but it do not happens always. Some of the austenite will remain untransformed, so they will remain still as austenite at a low temperature or room temperature or below room temperature, right? So that means at the end of the process you will be having martensite and retained austenite. And retained austenite is a very soft phase, martensite is a very hard phase. So you understand the failure may start from the austenite portion, right? Because it is soft phase, the strength is less, so the failure may start from the austenite portion. So it is not good, right? That is one part. And the part is this residual stresses in the steel may arise. How residual stress may arise in the steel? Because these austenite, after a long interval of time, they may decompose into some other phase. They may decompose into benite or some other phase, right? So that means phase transformation of this retained austenite may takes place after some interval of time, right? So due to this phase transformation, what happens? The volume change will occur. Austenite have a certain volume. The new phase which will may form, the benite may form, or you can convert some other phase. So due to phase transformation, the volume will change. Once the volume will change, you understand you are generating some stress inside the material, right? Obviously, the strain will generate. If the volume will change, the strain will generate. That will give rise to some residual stress in the steel. And once the residual stress will be there, and that will be the failure side. The failure may start from there, right? So these are the limitations. Next, we'll discuss about the steel quality. So nobody will buy a steel of poor quality, obviously, right? Because customer never want that steel should be of poor quality. So quality of a steel will be determined by three things. The first thing is on the basis of how much impurities is present, and the impurities is mainly phosphorus and sulfur. That means how much phosphorus is there, how much sulfur will be there. That will decide the quality of steel. And another one is the oxidation. If oxidation of the steel will be more, that means the oxide scale will be more in the steel, the surface finish will be poor, the steel will not looks very good, due to poor surface finish, due to this oxide layer on the steel, right? Another one is you can, in another term you can say, uh, the steel should have all the oxygen present in the steel should be removed properly. because you understand the problem. Oxidation may happen anyways. And cleanliness of the steel means the steel should be more clean. More clean means it tells about the non-metallic inclusions. That means the non-metallic inclusion percentage should be very less or should not be there, right? Non-metallic inclusions are what? There may be oxides, there may be sulfides, there may be silicates, because these oxides, sulfides, silicates are harder phase, brittle phases or harder phase. They never deform, right? Steel is a iron. It may deform easily on on doing hot working or cold working, right? But these non-metallic inclusion never deforms, right? What happens? Can anybody, do you have any idea of what happens if you have non-metallic inclusion like oxides, sulfides, silicate in your steel when you are doing deformation? That means plastic deformation, or you are doing metal working. What will happen? Do you have any idea on this? Or during application, what will happen if non-metallic inclusions will be there?
So it will result to casting defects.
Casting defect. How casting defect? Casting defect always arises basically due to the presence of dissolved gases like nitrogen, hydrogen, oxygen, right? Porosity, blowholes, surface blows,
Sir,
hairline
that may
cracks.
cause
Yes,
cracks
yes.
and fatigue failure in steel.
Very good, very good. So, Sri, you know, very nice. So, what the issue? I just few seconds before I told you the reason. These oxides, the sulfides, the silicates are brittle phases, harder phase, very hard. You cannot deform them by plastic deformation. They will not get elongated, or they may get elongated at high temperature, but at low temperature they cannot be elongated. Steel can be deformed to a large extent. The plastic deformation can happen to the steel. So suppose you understand, suppose you are doing cold rolling, for example, and some non-metallic inclusions are present. So what will happen? The steel will deform to a large extent, but the position where this non-metallic inclusion is present, they will not get deformed. So what will happen? The stress distribution will be uniform or non-uniform. Susri, can you explain it? The stress distribution will be uniform or non-uniform during plastic deformation now? Obviously, the distribution of stress will be non-uniform. Why?
Yes,
Yeah, why non-uniform? Because one is very hard phase. Non-metallic inclusion is very hard, stronger. It cannot be deformed or very difficult to deform, but steel can be deformed easily. So the concentration of stress will be higher around the inclusions, non-metallic inclusions. Those are called stress riser or stress concentration site. You understand? The concentration of stress is higher around the inclusions, but not around the steel, right? So what will happen? If the concentration of stress will be more and more, the crack will initiate from the inclusion part and the whole material will get cracked. Due to that, the crack will propagate, initiate from those points, and it will get propagated, right? Or suppose anyhow you have make a steel and you are putting into application. So during application, when there will be a load acting on it, the distribution of load will be non-uniform, or distribution of stress will be non-uniform. The stress distribution will be more around the inclusions because they are hard and stronger, right? So again, the crack may initiate from the non-metallic inclusion points. The non-metallic inclusion will come out, right? They will come out from the matrix. So crack will initiate and propagate, and it leads to failure. I think you people understood the point. Okay. So now, so that means this non-metallic inclusions must be removed as much as possible. But if they will be present, we can modify their shape. We can modify their shape into spherical kind of thing, because spherical means the distribution of stress will be uniform, right, everywhere. But if it is elongated one, if it will be needle shape, then that is very dangerous, because if it is needle shape, that may have sharp points, and sharp points have high stress concentration, right? The crack may initiate from there. Maybe some higher lectures I may explain more about this, by showing you some diagrams. Okay, so this is
Hello,
very
sir.
interesting. Yes.
Sir, by heating or annealing, can we remove these inclusions?
Heat or again, can you repeat?
So by heating or annealing, can we remove these inclusions from
No, no,
microstructures?
no. How just by heating you can remove them? They are already present in the material. How you? That means you are saying they get volatilized. They will not get volatilized because their melting point is very high. Oxides melting points, the sulfides, these silicates melting point is somewhat high. Silicates have low melting point anyhow, but oxides and sulfides have high melting point. They cannot be removed by doing melting or sorry, they cannot be removed by doing heat treatment. You can modify their shape. I told you can change the morphology of those things. If it is an elongated one, or if it is a needle shape, you can modify it into spherical shape, spheroid form. Spheroid form means concentration of stress will be uniform everywhere. It is a spheroid, right? Or you can do what? You can break them into smaller pieces and you can distribute them everywhere because they basically segregated in some particular locations. So you need to break them into smaller pieces and you can distribute them everywhere. That can be done by rolling process. In the rolling process,
Sir,
yes.
sir, with changing this morphology of this inclusions means the strength increases of the steel or
Yeah. The strength, inclusion sometimes is advantageous because if inclusions will be present in a very small size and there is a better distribution of inclusions throughout the grains, then that is beneficial sometimes. But if it is detrimental or if it will give you ill effect if it is a bigger in size and or if it is having a sharp ends like needle shape or if it is in elongated form, they are detrimental or deleterious to the property of the steel, right? Okay, so we can have high quality steel, we can have ordinary steels, we can have a quality steel, depend upon the weight percentage of phosphorus and sulfur. It is written over here, right? Okay, today we'll move to the last topic, that is segregations. You people understood what is segregation means. You have a better idea, I think, but let me tell you again what is segregation. Segregation means there is a non-uniform distribution of alloying element, or there is a non-uniform distribution of impurities elements present in the steel, right? Segregation means non-homogeneous distribution of alloying elements or impurities elements, right? That means starting from the center of the grain, if you move toward the grain boundaries, you find that the alloying element concentration is different. It is not same. That is called segregation. Hmm. That means, or in other words, some people call segregation has happened. What it means? That means the alloying element has segregated in a particular position. Suppose along the grain boundaries, right? So non-uniform distribution of alloying element or non-uniform distribution of impurities element is called segregation. They have been segregated at a particular positions, particular locations. So obviously the property will be poor, obviously, right? So basically there is a concept called microsegregation. So microsegregation means suppose you have a liquid steel now and its composition is C0. That means everywhere in the liquid, the alloying element are well distributed, right? But the moment you start solidifying the liquid steel, what happens? You understand. Okay, can you people tell me which kind of structure will come out upon solidification? I think I told you during your solidification part in thermodynamics, advanced thermodynamics class. If it is an alloy, which kind of solid will come out? The cast structure will be what? For an alloy, the cast structure will be what? Upon solidification? Dendrites will be formed. You have forgotten everything. The dendrites will form. Because if you're dealing with a pure metal, then you will get a simple like your EQX grain, it may form. Or if it is a homogeneous, if it is a normal kind of solidification, you may end up with your fine EQX grain along the mold wall and then columnar grain. Then finally, at the center, you may end up with big EQX grain, right? But if you are doing heterogeneous nucleation, you can end up with your what? That is EQX grain everywhere, right? But we are dealing with alloy, right? Once you are dealing with alloys, upon solidification, we are end up with this dendritic structures. Dendrite means it is a tree-like structure. It has many arms, primary, secondary, tertiary arms, right? You have seen that, I think. I remember you have seen that. So problem is what microsegregation happens. Microsegregation happens means what happens? when the dendrite will form from the liquid steel, dendrite is a solid structure, it will start rejecting solutes. It will start rejecting the alloying elements. So where the alloying element will move? Alloying element will obviously move towards the liquid, right? So dendrite is a solid. So that means you can imagine the situation. You have a mold, and in that mold, your liquid steel is getting solidified. So dendrites will form. So when the dendrites will form, that is a solid, it will start rejecting your alloying elements into the liquids. So finally, that liquid will get solidified, right? So the final liquid which will solidify, they have different compositions of the alloying element. They may reach with, they are more richer with your uh, alloying elements. The concentration of alloying element will be higher compared to that of initial initial composition C0. It may become C1, right? So obviously property will be deteriorates because because the distribution of alloying element is non-uniform, right? It is already written over here. You can read it. So now there is the important point here I have written. Partition coefficient between solid and liquid, which is K, is very less in case of phosphorus and sulfur. Partition means, you understand, distribution of alloying element in solid and liquid, right? So if the partition coefficient between solid and liquid is very less in case of phosphorus and sulfur, but it is not less in case of manganese and silicon. Can you people tell me what is the consequence of this? If the partition coefficient is less for phosphorus and sulfur, but high for manganese and silicon, what will happen upon solidification? That means there will be more segregation of phosphorus and sulfur will be there, because partition coefficient is less. If partition coefficient will be less, they will be not uniformly distributed in the liquid and solid, right? That's why phosphorus and sulfur will always get segregated. That is for microsegregation. But manganese and silicon will get segregated somewhat, but the amount will be less because the partition coefficient is more, right? I have written the problem associated with the microsegregation. The quality of cast become poor, right? And during solidification, the solid cell thickness is low. This is another problem. And depth of the mushy zone is more. Here I have written the nature of segregation is more for phosphorus and sulfur, but less for manganese and silicon because of this reason, partition coefficient. And already I have discussed you about the problem with phosphorus and sulfur and all. Okay. So this is the end of the lecture. If you have any doubt, you can ask me.
Sir, can you repeat that partition coefficient?
Partition coefficient means, partitioning means the distribution. How the alloying elements or how the impurity element are getting distributed in solid and liquid. Partition coefficient comes when you are doing solidification. The liquid will get solidified into solid, right? Now you got the point?
Sir, means the concentration of solid in liquid and solid. That.
Concentration of alloying element in solid and liquid,
Okay, okay.
right? If it is less, then that means phosphorus and sulfur will have a poor partition coefficient. Phosphorus and sulfur will be more in the solid, more in the liquid and less in the solid. You understand? So more in the liquid means, so that liquid will also get solidified at the end of the solidification. So that liquid which will solidify at the end of the solidification will be more rich in phosphorus and sulfur. Because the initial dendrites, they will start rejecting the solute. They will start rejecting the phosphorus and sulfur more and more.
So, which is undesirable.
Obviously undesirable. I told the problem. What is the problem with phosphorus and sulfur? Hot shortness and cold shortness. Okay, any doubt you have, you can ask me. I have no problem. I can explain it again. Okay, I think there is no doubt.